Good morning, or good afternoon for our European guests. Welcome to the first in what we plan to be a regular series of topical webinars. These webinars are designed to help you with your understanding of the theory or applications related to the use of products offered by Mirion Technologies. My name is Doug Van Cleef, and I'm responsible for helping our services team to develop and deliver services to you, our customers, with the specific purpose of helping you do what you do better. This is my first attempt at a live webinar, and my colleagues have strapped me to a chair, which I'm totally unaccustomed to, so I hope you will bear with me as I fumble my way through this. In today's seminar, Introduction to Gamma Spectroscopy Fundamentals, we will only be able to scratch the surface of the content. To help us to be more effective at that, we have asked you to let us know your preferred topics, and you've done a great job choosing these topics. So we will proceed by reviewing each topic, followed by a short Q&A period, then answering some questions we've received in advance, and finishing with an open Q&A period. As you have already seen, for the Q&A, you can submit your questions in the chat box. And yes, I have a moderator to protect me from my so-called friends out there. I do want to apologize to all of you for the video. I asked my production team to turn off the camera to enhance the appearance of the instructor, but they refused. You should also be aware that I will occasionally introduce some shameless promotions, because after all, we have to pay for these seminars somehow. In fact, I'm going to start with a shameless promotion about training. So why do I care about training, and why do I think you should care about training? Please note that although I think I can give you some really good reasons for choosing your training from us, it's even more important to me that you get good training from somewhere. Why? Every professional skill needs a solid foundation. The skill sets required in our industry are unique. The instruments and software in use today are complicated. Technicians and specialists have more to do and less time to learn how to do it. We have fewer experienced or expert technologists in our labs to help mentor us. And finally, a well-trained employee is a more efficient employee, a happier employee, and is more likely to be retained. I think this illustration pretty sums up my perspective. What do you think? If you think you could use some training, we'd be happy to help you, and we have lots of ways to do that. We've put a great deal of energy and technology into our training programs in the past few years, and we'd love to have you check that out. Let's get started. I believe I can touch on and illustrate all of the common gamma ray spectrum features in 13 minutes or less, but you will need to listen fast. Are you ready? The three top subjects submitted by webinar registrants were gamma spectrum artifacts and interpretation, reporting and interpretation, and calibrations. We will take a quick look at all three of these topics, starting with the most popular choice, highlighted here in red. To help illustrate this content, I have taken some images from one of my favorite teaching sources, the INL Spectrum Catalog. Though the nuclear data in the catalog is not current, the decay scheme presentations and spectral data is great for teaching and for this particular topic. To introduce the topic of gamma ray spectrum artifacts, I'm going to use this very convenient aluminum 26 decay scheme, which all by itself gives lots of spectrum features to discuss. But before we proceed to the spectrum view, please note that aluminum 26 decays by positron emission, followed by gamma ray emission to the ground state of magnesium 26. It is common to illustrate this by having the decay scheme drawn to the left of the nuclide, as you can see here on the screen, where it is common to show beta minus decay by having the decay scheme shown to the right of the nuclide. On this slide, we see a nice collection of spectral features just from the decay and gamma emissions of aluminum 26. We will discuss each of these features one by one, using a simple review of the physics of the measurement process as the reason for the appearance of the feature in the spectrum. You may wish to note that the INL Spectrum Catalog has a horizontal axis in units of channels, with the peak energy values in keV listed on the spectrum display itself. With that, we will start with the physics principles now. The first we'll mention is the photoelectric effect, in which all of the incident gamma ray energy is transferred to the ejection and kinetic energy of an orbital electron. The electron is released with kinetic energy equal to the initial gamma energy minus a small amount of electron binding energy. I call this our favorite interaction mechanism for gamma spectroscopy because all of the energy of the gamma is transferred to electrons, resulting in a measurable electrical current that is directly indicative of the gamma ray energy. Albert Einstein published a paper on this in 1905, which eventually led to his only Nobel Prize. And you thought he got that for relativity. What year did he get that Nobel Prize? In 1921, 17 years after he wrote the paper. Seems like a long time to wait. If all of the gamma rays interacted with our detector only by photoelectric effect, all we would get is full energy observation of the interaction. When we have a collection of observations, we call that a peak, thus the name full energy peak. Note that even for higher energy photons that do not interact primarily by photoelectric effect, we can end up with a full energy observation, as the other interactions that are possible may finish with a photoelectric event. On the surface, Compton scattering is the least desirable form of gamma ray interaction because it may result in an indiscrete amount of energy being deposited in the detector, and it is the most likely interaction in the energy range that most of us work in. The energy deposited by a gamma ray undergoing a scattering interaction in the detector is predictable based on the initial gamma ray energy and scattering angle. The scattering angle is also predictable based on the initial energy, with higher energy gammas tending to scatter in the forward direction. We can get into a lot more detail about how this works, but not today. If a gamma ray enters the detector and undergoes a series of Compton interactions, finally resulting in a photoelectric event, we get an observation in the full energy peak region. When a gamma ray enters the detector and undergoes one Compton interaction and then leaves, there is a maximum amount of energy that can be deposited. That maximum energy deposition occurs when the gamma is scattered near 180 degrees. This physics principle results in a spectral feature called the Compton edge. Lesser amounts of energy deposited by Compton interactions result in the feature we call a Compton continuum. When a gamma ray enters the detector and undergoes multiple Compton interactions before leaving, the deposited energy is summed and may fill the valley between the full energy peak and the Compton edge. The primary interaction mechanism for high energy gammas is pair production. In pair production, we see a real-world example of energy and mass equivalence, as an electron and positron are produced with total rest mass plus kinetic energy equal to the energy of the incident photon. At least 1022 keV is required for this interaction, because that is the combined rest mass of the positron and the electron. Any excess photon energy above 1022 keV is converted to kinetic energy of the electron and positron, which will cause release of other electrons through secondary ionization. It should be noted that the secondary ionization produced by the kinetic energy of the positron and electron will always be captured in the detector after a pair production event. Therefore, that's the minimum amount of energy that will be captured in that interaction. The positron will combine with an absorber electron as soon as it comes to rest, annihilating the positron and that electron. Two photons are then emitted in opposite directions, each with 511 keV, equal to the rest mass of an electron. One or both of these annihilation photons can escape the detector, not allowing the full energy of the original incident gamma ray to be deposited. Once again, the only way to measure the full energy of the original incident gamma is if both of the annihilation photons deposit all of their energy within the active volume of the detector. If a gamma ray enters the detector and initiates a pair production, pair annihilation event, and the energy of both of the annihilation gammas are fully absorbed in the detector, we still get an observation in the full energy peak region. When a gamma ray enters the detector and initiates a pair production event, after which one of the annihilation gammas leaves the detector with no further energy deposition, we get an observation at the original full energy less 511 keV. If we get enough of these observations, we get a feature called a single escape peak in our spectrum. When a gamma ray enters the detector and initiates a pair production event, after which both of the annihilation gammas leave the detector without any further energy deposition, we get an observation at the original full energy less 1022 keV. If we get enough of those observations, we get another thing called a peak. In this case, it's called a double escape peak. If a gamma ray enters the detector and initiates a pair production event, after which either of the annihilation gamma rays undergoes Compton scattering and then leaves the detector, we get the same effect as Compton scattering alone. That is, an indiscrete amount of deposited energy and production of this thing we call a Compton continuum. And now for a quiz. You didn't know a quiz was coming today, did you? Where does the 511 keV peak come from in this spectrum? You have 10 seconds to consider your response. I'm going to open a poll for you to do that. This may take me a while. I'm not smarter than the technology. I'm sorry, there's my button. Okay, the poll is now open, and we can start our 10-second countdown timer. Ha, your 10 seconds is up, but it looks like 10 seconds wasn't long enough. A lot of responses still coming in, so I'll give you 5 more seconds. All right, sorry, time's up. We've got to move on. So I'm going to close the poll. Oh, WebEx tells me you have 13 more seconds. So we'll just wait a few more seconds. Dead air. I understand dead air is loved by everybody in this business. So, all right, so 89 of you found a way to get a response into us quickly, and I can show you the results of this poll somehow, if I can find the right button. There we go. I hope I'm showing the poll results. I'm getting confirmation in here. That's excellent. So it looks like 37 of you chose the first answer. That was the most popular answer. And only 2 of you suggested that might be a gamma ray emission from thallium-208. So let's talk about this poll. I'm going to close this now. If you want to go back and look at those results, you can go back and watch this video again later. So what's the right answer? You'll have to grade yourself on this quiz because I don't have individual statistics on who answered what. Note that, first note that the aluminum-26 decays by positron emission and it has high energy gammas. If you said that the 511 keV peak comes from pair production, pair annihilation in the detector, I'm sorry to say you failed the quiz. If you said that pair annihilation of the positron inside the detector was the source of that 511 keV peak, I'm also sorry because it's not possible for the positron to make it to the detector material. So that answer is out. If you said gamma emissions from the 510.8 keV line of thallium-208, well, you could be right, but this is in fact an aluminum-26 spectrum, not a thallium-208 spectrum, so we're going to eliminate that as the correct choice also. So if you said that the 511 comes from pair production, pair annihilation in the sample or in material surrounding the detector, or perhaps you said to yourself that the 511 comes from pair annihilation following this positron decay, you aced it. Since there's no mathematical way to come up with a 511 if the pair annihilation begins in the detector, it has to occur outside. And with aluminum-26, we have 2 highly probable ways for that to happen. We have the positron emission, which is always going to result in pair production inside the sample material because the positron isn't going to move very far. Or we have pair production, pair annihilation, which could be produced by these high energy gamma rays. And if that happens outside of the detector, we can get a 511. Okay? Let's move on. And finally, we will talk for just a moment about summing. Here, we show an obvious example of summing with 2 prominent collections of observations at 511 and 1808 keV, which sum to 2319 keV. But what about the 2938 keV observation? Is that a sum peak or a regular gamma decay peak? The answer is yes, it is both. If you look again at this aluminum 26 decay scheme, which I told you earlier I thought was a really good teaching example, we see that we can get the 2938 keV gamma ray from a single gamma emission directly from the highest excited energy state to the ground state. Or we can get a gamma ray from 1129 keV to the middle excitation state, followed by an 1808 keV gamma to the ground state. Either of these mechanisms add up to 2938 keV. Okay. Questions so far regarding spectral features that we can answer. We have a couple of minutes after each of these topics to answer questions. And I believe I have received a question. We got a question about whether or not the INL spectrum catalog can be found online, and the answer to that is yes. And we have, I see a link that has been provided for that. Did everybody get to see that link? I have to provide that link somehow. All right, I can do that, I think. Let's find out. I believe I have sent that link to everybody, and I have local confirmation, so very good. Any other questions from our moderators? All right, we're going to move on then, presuming I can overcome the technology and do that again. All right, our next topic will be calibrations. Reporting and interpretation actually received more votes, but the calibration concepts are important to the reporting discussion, so we will cover calibrations next. When we refer to calibrations for gamma spectroscopy, generally speaking, we are referring to three types of calibrations. The first type is an energy calibration, which provides a mathematical relationship between gamma energy and spectrum channel number and is essential for proper nuclide identification. The second type of calibration is often called a shape or resolution calibration, which provides a mathematical relationship between gamma ray energy and expected peak shape. In general, spectral peaks become wider as the gamma energy increases. This calibration is necessary to enable the peak fitting of wide or overlapping peak areas by the software. The third type of calibration is called an efficiency calibration, which establishes the relationship between gamma ray energy and detector response. That response is the mathematical equivalent of the ratio of gamma rays emitted from the sample and those fully absorbed in the detector. A different efficiency calibration must be performed for each unique sample type because efficiency will change with variations in sample volume, chemical composition, density, sample detector distance, container configuration, and many other variables which we'll talk about in just a moment. The efficiency calibration is essential for nuclide quantification. Without knowing the efficiency, we cannot get an accurate activity calculation. Okay. The energy calibration is generally the simplest of these, using a simple fit between the relationship, for the relationship between the MCA channel number and the gamma ray energy. We use that fit to assign energy values to every peak found in the sample spectrum for nuclide identification. The energy calibration equation is normally a simple linear fit which works well for most gamma spectroscopy applications. As I mentioned, the software uses shape calibration to determine the expected width of the peak based on the energy of that peak. This helps the software decide if the peak found is a single peak, as illustrated here, or part of a group of peaks, which we call multiplets. Having a correct expectation for peak width by energy also allows us to calculate a priori or before the fact estimates of detection limits, because the width of the peak directly influences the area of the background in that region of the spectrum. The peak shape or resolution calibration calculates the relationship between peak width and gamma ray energy expressed as an equation based on the square root of the gamma ray energy value. In general, peak width increases as gamma ray energy increases, but not as a linear function. Some software allows the use pardon me, got ahead of myself there. Some software allows the use of peak width instead of a fixed energy to be used for matching a gamma ray peak to a nuclide, which takes into account the increase of peak width as energy increases. In some applications, this can improve the selectivity of the peak and nuclide matching. Now on to efficiency. To introduce this topic, I'm going to play a short excerpt from our online self-paced Fundamentals of Gamma Spectroscopy training course. Then we will discuss a few of the important points about efficiency calibrations. And I told you I'm going to play a video. That presumes that I remain smarter than the technology, and we'll know that in just a minute.
For radiation detection measurements, we generally define efficiency as a mathematical relationship between the observation rate of a radiation event and the emission rate of that radiation from a calibration source or sample. For gamma spectroscopy measurements, we typically define and calculate full energy peak efficiency, also commonly referred to as peak efficiency or absolute efficiency. We can also define geometric efficiency, intrinsic efficiency, and total efficiency to each represent something different from full energy peak efficiency. But these other factors are rarely calculated directly during routine calibrations of gamma spectroscopy systems. When determining the full energy peak efficiency, only a fraction of the gammas emitted from the sample or source matrix will travel on a pathway that will reach the detector. Increasing the separation distance between the source of radiation emission and the detector will decrease the fraction of gamma rays that will intercept the detector. Of those gamma rays that do reach the detector, not all will deposit their full energy within the detector crystal.
Okay, I hope everybody was able to watch that. Please note that the videos in our online programs are much crisper than the ones that I'm able to play inside this webinar. Okay, for our purposes, we want to know the probability that an emitted gamma ray will interact with the detector crystal and produce a count or observation in the spectrum corresponding to the full energy of the emitted gamma ray. That's the full energy peak efficiency. In gamma spectroscopy, efficiency, full energy peak efficiency, absolute efficiency, and terms like that are generally synonymous with each other and highly dependent upon the sample to detector geometry and the energy of the gamma ray. There are some occasions when we need to use efficiency in a different term in gamma spectroscopy, but that's beyond the scope of this course. There are several important factors that affect efficiency, and all of them matter. If we don't have all of these correct, we will not get an accurate quantification of the nuclide activity. Those include detector and sample distance, offset of the sample from the detector axis, sample container dimensions, sample matrix characteristics including chemical composition, density, and fill height or mass or volume, and detector parameters such as detector crystal size and shape, detector end cap materials and dimensions, a dead layer if there is any on the surfaces of the detector crystal, and other absorbers which may be present between the sample and the detector. A simplified overview of the calibration process goes something like this. First, obtain a suitable source. Sources traceable to a standardizing body such as NIST are suitable for all three calibrations, the energy, the shape, and the efficiency, while non-traceable sources may be good only for the energy and shape calibrations. The gamma ray energies from your calibration source should cover the full range of gamma energies you will be looking for in samples. For each of the calibrations, acquire the spectral data for a long enough period of time to get very well-shaped peaks with low uncertainty. Most consensus standards recommend 10,000 counts or more to get a counting uncertainty of 1% or less. After the calibration, verify the accuracy by counting an independent but well-known standard, preferably a traceable standard, in the same geometry. The verification standard does not have to include all the nuclides used in the calibration, but should cover most of the calibration energy range. And of course, when you are done, make sure you have a thorough documentation trail. All right, what else do I think you need to know about efficiency calibrations? Well, by now you're probably aware that there are commercially available software packages that allow modeling of counting efficiency for gamma spectroscopy. Our products in that field are iSox and LabSox. The combination of conventional or empirical calibration techniques and mathematical modeling together can greatly enhance the utility of gamma spectroscopy systems, especially for unusual or unexpected sample configurations. As with empirical calibrations, modeled calibrations should be validated with an analysis of a known sample whenever possible. And you may be already aware that mathematical modeling techniques are now widely accepted by regulatory bodies and addressed in consensus standards. I'm going to give you a couple examples of those. In the NRC's Reg Guide 121, we have now language regarding the use of mathematical efficiency calibrations for nuclear power plant effluent monitoring. MARLAP, a very good reference, modern reference for radiochemists, also references the use of mathematical models. This manual contains guidance for radiochemistry measurements endorsed by a majority of federal agencies. And more recently, the EPA has published a very nice guide called the High Resolution Gamma Ray Spectrometry Analysis for Normal Operations and Radiological Incident Response Manual, which has a lot of great information in it, including a very useful discussion on mathematical modeling. And just in case you're wondering, yes, that's available online too. If you'll contact one of us at Mirion, we'll let you know how we think that you can get your hands on one. Okay, questions on the subjects of calibrations before we move on? I have a question regarding which applications a linear fit would not be appropriate, if I interpret that question correctly. Well, that depends on which calibration you're talking about. In the energy calibration, if you're not getting a linear fit, you might need to look at the condition of your electronics. That might indicate that you have some kind of a problem in your electronics. In the case of the resolution or shape calibration, it would be a little bit unusual to have a good linear fit at low energy, where a linear fit might perform reasonably well at high energies. The fitting function that is used in most modern gamma spectroscopy software is pretty good right now, and generally speaking, it allows you to pick or add an additional order of fit to those equations. So if you're not getting a good linear fit, you might want to increase the order of fit in your software. In efficiency calibrations, generally speaking, most modern software offers a number of efficiency fit methods, and the one you should pick is the one that gets your empirically determined efficiency to the closest match of your calculated fitted efficiency. At least that's in my opinion. And another question, can the calibration only be done in the expected range of nuclides, or does it encompass the entire range of energies? That's a great question. In a perfect world, you would use exactly the nuclide you're trying to analyze for every calibration, but that's pretty impractical. If you use a mixed gamma standard, such as is commonly provided by a popular provider in Atlanta, then you're going to have a broad range of available energies, and the fit of the efficiency to those energies is pretty good using that. If you have samples that are prone to, for example, coincidence summing, those sources tend to introduce a little bit of uncertainty for those radionuclides that are prone to coincidence summing. There are tools for correction of that, but generally speaking, if, for example, you have an efficiency calibration source whose energies range from 60 to 1836 keV, any of the gamma ray emitters in that range, you would get pretty close to the right answer by using a standard commercially available source and not having to apply any additional corrections. There are certainly plenty of exceptions to that. Many of you on this webinar probably are aware of those. If you want any more detail on that, please drop me a note and I'll try to address that for you. Okay, ready to move on? Move on we will. Good questions, thank you for those. Okay, the last topic is reporting and interpretation, and we'll jump right in there. We'll start with a brief commentary about overall reporting considerations. here's my opinion about this. If the big picture question should be, if I need to defend these results contained in my report 10 years from now, and no one is around to answer questions, do I have enough information in the report itself to believe the results? Another important question is, can a user of these results use them for the intended purpose? And finally, if I endorse these results, will they come back to embarrass me later? So, how do we decide if this report is going to keep us from being embarrassed, give us results that the end user can use, and we'll have enough information to be able to reproduce it later on? Let's start with the header information. I think of this as your first reality check. And here what we should do is look at things like the sample information to make sure that it's correct. That's going to include things like the sample name, the identification, where it came from perhaps, the sample form, liquid, solid, something else, and the geometry that it's in. We should also find sample information related to dates and times. We should be able to validate those through our chain of custody or whatever mechanism we're using to track our sample back to its source. We should also take a look at analysis parameters. How is the software set up to do the analysis that we're about to conduct? Does it follow the appropriate SOP? Does it follow the appropriate data quality objectives if they're listed for this particular procedure? Does it follow the client statement of work? These are the kind of considerations that we should be able to answer with a review of our header information. Then we move on to some of the calibration information, which I consider to be the start of technical defensibility for an analysis report. We should be able to have equations, or at least pointers to where we can find the equations for our energy and our shape calibrations. We should also have, either in the report or in something in the report that points to where I can find this information, efficiency parameters, so that if I choose to, I can confirm the efficiency at individual energies. Proving the efficiency calculation may not be as easy as it seems. It is up to the user to know the equation and the units. And I want to just give you a quick example of why that may be more difficult than it seems. Here you see on this particular report that the natural log of the efficiency is equal to the offset plus the slope times the natural log of the energy plus the slope times the natural log of the energy squared, and so on. Well, that gets us an answer as the natural log of the energy. That's really not what we want in practical terms. We can convert that equation to the one I now show at the bottom of the page, where efficiency is E raised to all those parameters in order to get an absolute efficiency number. That's probably not a calculation you're going to do on your calculator or by hand. So more than likely, you'll need to set up a spreadsheet or something like that to do your efficiency checks in your reporting. Okay. When we get to the peak search or peak locate report, now again we have the opportunity to think about consistency of sample information or consistency of analysis parameters. Are we doing everything the same here as we said we were doing on the header page? We can do a spot check of the energy calibration. We can take those energy calibration offset and slope, multiply it by the channel number, which is listed here, and we should come up with the energy that is listed here. This particular report also gives us an opportunity to look at peak significance, where we can compare that significance value to the user-selected sensitivity. Generally speaking, if the peak significance is below the user-selected sensitivity, we may not be interested in the presence of that peak. I personally think it's a good idea to spot check each of the calibrations with some routine frequency, maybe every 10 or 20 reports that get reviewed. Why? Because it would be a pretty bad deal to discover an error in the application of your calibration data after you've delivered a few hundred reports to your client. Okay. Next up is the peak analysis report. Again, we have the opportunity to look at consistency of sample information, analysis parameters, and we can do a spot check of the resolution trend. Since we expect the resolution to increase over increasing energy, we should see that demonstrated in our peak analysis report. Next up is the peak efficiency report. Some software generates a peak efficiency report, which an example of which is shown here. I think it's a good idea to spot check this also, although I've already indicated it will probably require you to maintain a simple spreadsheet. Note that when you do that, if you choose to do that, whereby you take the energy and you plug it into that equation that we just showed you, you will end up calculating an efficiency number. More than likely, you're not going to match that efficiency number exactly, but you should match it to at least the first, possibly the second decimal place. The reason for the difference is not because it's being done incorrectly. The reason for the difference is that the software is using more significant figures than it's showing you on your report. So. On the nuclide identification report, which of course is what the final objective is, this is why we do gamma spectroscopy, to get our nuclide identification report along with activity results. We should again look for consistency in sample and analysis information. We should check for consistency in nuclide information. There are collections of nuclides which might seem mutually exclusive. For example, if we've got a solid sample with a bunch of particulate matter in it represented in our nuclide report, we might not expect to find a krypton-85 gas also showing up in our report. We might also look for consistency in the activity reported from different lines of the nuclide. In this particular example, we see the reported activity for the two lines of cobalt-60 to be very similar to each other. We should expect that. There are legitimate reasons why they might be dissimilar. For example, if an interference correction has been applied, or if coincidence summing causes something to change, but that's beyond the scope of today's discussion. Generally speaking, the last thing to come out of a common report is something we will call an MDA report. It is common in our industry to generate an a posteriori or after the fact MDA report with our results. Most of the time, this report has no value whatsoever except to satisfy a misunderstood expectation that will generate this report. What might be valuable when counting samples for activity at low levels is the use of a decision level or decision threshold to help with detection decisions. As a charter member of the I Hate the MDA committee, I believe I have some useful recommendations for the MDA and critical level. I'd be pleased to share that with you if you'll contact me after the course, or you can ask a question in the chat box, which we'll get to in a few moments. Or you can get this information from one of our online or instructor-led courses. Better yet, for those of you looking for a good excuse to come to the west coast of Florida this summer, we'll be doing a full-day seminar on this topic of reporting at our Mirion Connect conference, formerly known as the Users Group Conference. And that training session will include a thorough treatment of MDA, decision level, and detection decisions. On this particular report, in the right-hand column, you see a column for decision threshold, and next to it you see the activity. If you wanted to use some kind of an indicator on this report to decide whether that radionuclide was present or absent, it would be by comparing the activity to the decision level or decision threshold as shown in this report. Generally speaking, we complete our report with a thing called the case narrative, which is basically just a written summary to clarify anything in the report that might not be obvious, but is essential to a proper understanding of the reported results. In this particular example, we see that the generator of the report wrote a short narrative, a short story about the way they analyzed radium-226 through lead-in-bismuth-214 and observed that radium-226 is difficult to identify directly because of potential interference with uranium-235. This is the kind of information which is not obvious in a report that's generated by gamma spectroscopy software, so it's a good idea to go ahead and add some commentary about that. Okay, questions on the subject of reporting before we move on? I'm looking to my moderators, and they're either rejecting your questions or we're just going to move on to an open Q&A. All right. We did get just one question, incredibly, in advance from an attendee, and I want to address that one while we're waiting for the possibility of additional questions. One of our customers, Jessica, sent us a question in advance. And Jessica states, our laboratory is shifting from using detection limits to critical values in order to be in compliance with MARLAP, FIRMAC, and NARL when we report results for environmental samples or emergency response. It is easy to get a sample-specific a posteriori MDA out of APEX. However, federal partners are interested in critical levels and not our MDA. Now, those of you who know me to be a member of the I Hate the MDA committee probably think this question is a plant. It's not. Jessica really did write this question, and Jessica, it's a great question. Thank you for submitting it. I have to say I'm really encouraged that your federal partners and you want to report the critical level and not the MDA. I expect my fellow members of the I Hate the MDA committee are happy to hear that also. Fortunately, the answer to this is relatively easy. The decision level is a core part of every a posteriori analysis and is calculated and stored with every result generated by Genie. For example, the decision level can be shown by running the standard ISO 11929 MDA report, which has a dedicated column for reporting the decision level. There are other ways to do that with other MDA reports, but that's the simplest. So the information you're looking for is there. The trick is to make sure you configure your report to display that information. Our tech services team can help you with that, and you can find contact information for them either on our website or from anybody in the company because we all know how to reach them. Very good question, and I thank you for that. More questions? Do you want me to review the question on constant calibrations? Is that the one that you're referring to? Scroll down. I don't see anymore. I think I have questions coming in, but I'm having some technical difficulties and do not see them. So. Oh, we have a backup plan. It's a great question. How often? The question is, how often should we do these calibrations? At least I think that's the question. Sorry for the little technological delay there. It's a great question. Most of the existing consensus standards have recommended calibration check frequencies in that. Obviously, when you set up a brand new system, all of the calibrations have to be done initially. After that, if you have some kind of a consistent, ongoing quality control and quality assurance process whereby you are checking parameters to ensure that your energy is not changing or the channel number of the peak locations is not changing, that the resolution is not changing, and that the efficiency is not changing, which are common parameters measured in daily or weekly or other frequency quality control checks, as long as your quality control checks so that you show that your detector is stable, I do not think there is any need to go back and do a calibration again. Some of the early ANSI standards published back as far as 1978 have been misinterpreted to suggest that these calibrations need to be done more frequently than that. But I think as long as you have a quality control process that shows that those parameters have not been changing over time, you're good to not continue to do calibrations. The next question is, what about drifting spectrum and calibration? That's a tougher question. If you have a reason to have your spectrum drifting, especially on a high purity germanium detector where that it should not be drifting, then you have a little bit of an instrumentation problem. You could certainly correct for that by doing an energy calibration immediately before you do a sample analysis and then doing another calibration check immediately after a sample analysis to make sure it was stable during that period. But in general, that suggests an instrumentation problem. Now, if you're using scintillators for your gamma spectroscopy, then you're going to naturally have some drift, especially if you have temperature changes. And then the answer is really the same. If you take a detector, for example, out of a laboratory into the field and you have a change in temperature, immediately before and after the analysis measurement is made, you should do an energy calibration check so that you can at least quantify any changes in peak position during that analysis period. And the third question is, why are different nuclides reported in NID versus MDA? And on this particular example, I don't know the answer to that. It is not, however, I'll make a maybe an educated guess. It is common to report the nuclides as found, and then it is also common to report the MDA, even though it may be inappropriate for the measurement. It is common to report the MDA perhaps for all of the nuclides in the library or all of the nuclides in the statement of work or something like that. So you may be getting an MDA report that includes everything you might have looked for, while on the NID report, you're only reporting what was actually found. I hope that answers that question. Any more questions? All right, very good. All right, this concludes our live webinar. We really appreciate you taking the time to join us today. Be on the lookout for an email announcing the second webinar in this series, which will focus on one of our newest products in the Mirion family, the Transportable Radiation Analysis Counting System, or TRACS. This seminar is scheduled for March 28th and will feature our Gamma Spectroscopy product manager, Kara Phillips. Please remember that all of our webinars will be archived and available on our website shortly following their broadcast. And lastly, since we focused a bit on training today, I should mention that we're running a sale through March on all forms of training that we offer. A link for that training promotion is now being sent to the webinar chat box. I also want to point out that those of you who have submitted questions that we did not answer here, we will answer after the webinar is over, and we'll continue to do that if you want to send questions to us directly. So I thank you very much for your attendance, for your participation, for the questions, and I hope that you all have a great day. Take care.